Now we're going to be turning our attention to useful distributions. The first and most common distribution that we will be using is the Gaussian distribution. The Gaussian distribution is also called the normal distribution, and you've probably heard it referred to as things like a bell curve. It's by far the most widely used distribution to describe a random variable, simply because it is very easy to implement. The equation for the Gaussian distribution or the normal distribution, the PDF, is given by this equation here. It is what we call a two-parameter distribution. Two-parameter distribution means that we have two parameters that we use to describe it. We have a sigma here and here, and we have a mu. X is our random variable. Now, the standard deviation is the width of the distribution, and that's what this sigma is representing. So we're consistent with what we've talked about in previous lecture. And mu is the mean or the central value of the distribution. So the two parameters to describe this distribution are sigma and mu. The notation in the textbook, when we describe a distribution and its parameters, we use this notation. And n standing for normal distribution, and then we use a parentheses with our parameters in there. So the parameter order that we use to describe the normal distribution is the mean, or mu, and sigma, standard deviation. These two parameters control the location of the distribution and its shape. So turning our attention here to the left-hand figure, we've got our PDF plots of three different distributions. These are all normal distributions with a mean of 60 and the standard deviations of 10, 20, and 30. So notice as we have just the general shape of the Gaussian distribution is symmetrical about the central value. And the previous equation on the previous slide is valid for minus infinity to plus infinity. So in fact, this distribution goes on to minus infinity and plus infinity, although the probability density, once you stray too far from the mean or central value, becomes quite low, extremely low. In other words, the probabilities are very, very low that the values would be taken up by their random variable. So the first distribution here, the dashed one, is a distribution with a standard deviation of 10. And we see that for this case it is relatively thin and high peaked. As we increase the standard deviation now to 20, we see that we get a spreading out of the distribution. That's the solid line. So our peak comes down a little bit. Again, we're staying at the central value of 60 for this example. And as we increase the standard deviation, the shape spreads out, so we now get larger amount of density or probability associated with numbers that are farther from the mean value, farther from the central value. And as we see, as we go to 30, if we increase it again, we get it even more spread out. And of course, this trend would continue in either direction. If we reduce the standard deviation, then we really become tight around some central value. Or if we make a very large standard deviation, then we become extremely flat. And the probabilities are spread out over a large range of values. The figure on the right keeps the same standard deviation but changes the mean. So in this case we have the normal distribution of that we have here with the standard deviation of 10, but the mean value is changing. So the mean value is 60 for this dashed line here, and then we change the mean value or the mu parameter to 45, and we see that we keep the same shape, but we shift the distribution to that centralized value of 45 now, where it was at 60. And then if we reduce it to 30, we change it to 30, then we shift it again, and the shape stays the same, but we simply just are moving the distribution. We're translating the distribution along the real number line with our values of x on the real number line. So it's a two-parameter distribution, and these two parameters change the location and the shape of our distribution, of the densities of the probabilities. This leads us to the standard normal. So if we say that we have a standard deviation of 1 and a mean value, or a central value of 0, then our equation that we presented before reduces to, or simplifies to, this expression here. So this is the equation for the PDF of our standard normal distribution. You can see the sigmas have dropped out because they become 1, and then the mu drops out because it becomes 0. Again, this is for minus infinity to plus infinity. The standard normal is a very useful rendering of our Gaussian distribution, as we'll see shortly. It's very commonly used, and because it's very commonly used, we give it a special symbol, and your textbook adopts this symbol. This is pretty universal. So the CDF of the standard normal variate S, because now we're gonna use S as kind of the random variate symbol, because we're talking about a standard normal, so we use S. The CDF function, which we described in previous lectures as being capital F S, this is capital S, so this is our random variate S of S taking on any value S. We give it a different symbol, and all we do is we say that it's phi of S. And we use this because this is such a commonly used way to describe random variables that the statistics and probability community have come up with this convention where they'll use this symbol, and your textbook adopts this as well, to describe the standard normal. So the standard normal is the Gaussian distribution simply with the standard deviation equal to 1 and the mean equal to 0. So then our equation becomes this simplified expression. The standard normal, again, this is a bell-shaped curve, but now the central value is equal to 0. So we're symmetrical about 0. And we have a standard deviation of 1. So we get some spreading out of our distribution to look like this. Now, the shaded area in this figure, which I will note that your textbook mistakenly calls this figure a CDF, when in fact it is a PDF. So it's an error in the notation of the figure only. They refer to it in the actual text correctly as the PDF, but the figure notation is mistaken. So if we are interested in determining what are the probabilities associated with values, and again we're using the standard normal here. So if we are looking at the probability that's associated with some value, what we can say is that, let's say, all right, we've got this shaded area which represents some probability, and remember, all the areas for all PDFs, the area under all PDFs is equal to 1. And that doesn't change whether we're Gaussian or standard normal or any other distribution that we'll talk about later in this term. They're all equal to 1. The areas are all equal to 1. Remember that. So if we are interested in some probability underneath our standard normal that's associated with some value S sub p, what we say is that the shaded area below the curve is the probability that the random variable S will have a value of S sub b or less. All right, let's say that again. It's this probability that's shaded in this figure tells us that the random variate S, the standard normal random variate S, will take on a value of S sub p or less than S sub p. That represents all of this shaded area. And we can look at this and we also see that, well, this starting from S sub p and going to minus infinity, this shaded area is some probability p. Well, I know that the entire area is equal to 1. So in fact, what I have is the case where this probability of the white area is actually equal to 1 minus p. Because I know the area underneath the standard normal is equal to 1. If I know that this probability is p, then the white area here has to be equal to 1 minus p. So what 1 minus p represents in this discussion is the probability that the random variable S is greater than SP. So we can also kind of switch this around and say, well, the value of the standard normal variate S sub p is the probability p that's denoted by this relation. So before we said, well, the probability p that the random variable S will have a value of S sub p or less is shown here. Well, what about just the opposite? Instead of giving getting the probability out of that question, what we want to do is get the value S sub p that's associated with this probability. So the top wording is the probability that's associated with S sub p. The bottom wording is the S sub p that's associated with this probability. So we do that by this notation here. We say S sub p is equal to the inverse CDF function for the standard normal variate of the probability p. So the value of S sub p is going to be the inverse CDF function. So the CDF function gives us the probability. The inverse of that would give us the value. So the inverse of the probability would give us the value. The textbook conventions for the standard normal variate CDF function phi is in this form here. Generally, S is the generalized random variate value S. S sub p is just, in this particular example of that figure, is just relating this probability p with this value S, and they say so S sub p. But in general, it's S, it can take on any value, is equal to the inverse CDF function of the probability p, but it can also be equal to the negative value of the inverse function of 1 minus p. All right, so let's look at that in kind of this figure here. So we said before that the value S is going to be the inverse of the probability. So if this is the probability, the inverse CDF function would give us this value. We can also find it by taking the inverse CDF function of 1 minus p. So remember in the last slide I drew up that this area here is equal to 1 minus p. Well, the Gaussian, or the standard normal, is symmetrical. So if I draw in here as best I can here a straight line, dashed line, S to p, so let's say this is minus S p. So this is the same value, the same distance, but in the negative sense. So this value of minus S sub p has a probability associated with it that's this hatched area from this value down to minus infinity. This value of probability is exactly the same as the white area because of symmetry. So this was equal to 1 minus p when we said it was greater than s sub p. So if we take the minus value of sp, which brings us to here, it's equal to the probability, this inverse CDF function of 1 minus p. So that's where this idea comes from. There's two ways we can find it. The other thing that your textbook uses is a negative value of s. So in this case, we have, as I drew up, a minus s sub p. This would be equal to, if we have the CDF function of a minus s, it's the same thing as 1 minus the CDF function of the positive s. So 1 minus the CDF function of a positive s, well, what is the CDF function of s? Is the probability. It is the probability. So this is equal to, the CDF function of a minus s is equal to 1 minus the probability here. It's exactly what I drew on here. So this is 1 minus the probability of the white area. So a minus p, as I illustrated before, is this hatched area. So to get this area is equal to 1 minus p is simply this relation here. And we use this relation because your textbook tabulates the standard normal probabilities for positive values only. In the back of your textbook, table A.1 lists the standard normal probabilities of, unfortunately they use x, and they should be using s for all of these because this is really the standard normal variate. And to keep things consistent, they should use s, but they don't, they use x. So the standard normal variate is given only for positive values. So the table reads in two-column batches here, and I've just clipped a small portion of this for illustrative purposes. We've got x, and we've got the CDF function of x. So it starts at 0. So the CDF function of x equal to 0 is 1/2. And that makes sense because our distribution is symmetrical, so it's exactly 1/2 probability. And remember this, by definition, the CDF function of a random variable at half is equal to the median. Remember that. So then it tabulates a number of values in increments. They get coarser as the numbers get higher, but it increments on up for about 4 or 5 pages of tables. And what you do is you look up the value x, and as you find the value x, let's say for 0.05, that would be something just greater than 0 in this case, right over here, let's say. Then it tells us that the CDF function of x is equal to 0.5199, let's call it 0.52. That tells us that the probability that's associated with 0.05 would be equal to this shaded area. And that is roughly 52% of the total area underneath the curve. But what if we had a minus 0.05 here? Well, your textbook doesn't tabulate that. And the reason is it's just due to symmetry, and they're saving space. And this is where this relation comes in. Well, if I have a minus 0.05, all I simply do is say 1 minus the CDF function of the positive value. So then I would take this and take 1 minus that to get what would be my CDF of the negative value of it. That's great. That table is great for a normal distribution, a standard normal distribution where our mean is 0 and standard deviation is 1. But what if we have some normal distribution that we don't have the standard deviation equal to 1 and our mean isn't equal to 0? What do we do then? How can we still use the table that's in the back of the textbook? The way that we do that is we have to transform x into s. Right? So figure 3.8 in your textbook, as drawn here, tells us or shows us an example where we have some normal distribution with a mean and a standard deviation. It's not a standard normal. Notice here's the 0. The mean is a positive value and it has some standard deviation. And what you may want to find out is what's the area between A and B, or between B and A, because this represents a probability that X, the random variate, takes on a value that's equal to or less than B but greater than A. That's this shaded area. The way that we could find that is, well, we could just directly go into our Gaussian distribution PDF and do the integration from A to B. But that's sloppy and that's difficult, and we've already got tabulated values, so why don't we do something a little bit easier? And the way that we do that is we transform the random variable X into S. So we're going to transform this into S. And the way that we do that is we say that S equal X minus mu by sigma. So that's this in here. And then we say dx is going to be equal to sigma ds. And when we do that transformation, we now get the value, the probability in normal distribution in this form, which is our standard normal. This is our standard normal distribution with now parameters of b minus mu by sigma, excuse me, not parameters, limits of integration, and a minus mu by sigma. So this is the standard normal, and what we're doing is we're taking the standard normal integration to these limits, so we can simplify it even further by saying this is the CDF function of now b minus mu by sigma minus sigma, the CDF function of a minus mu by sigma. So we've transformed the original problem, which was looking for, in terms of X, we were looking for the probability that X is going to take on a value less than or equal to B, but greater than A. And this is a normal distribution. And we transform it into this expression, which gives us the standard normal. And now it allows us to use the tables in the back of the book. So now we just have to plug and chug here the B minus the mean value divided by the standard deviation to get what value we would look up in our tables. And we subtract off of that the CDF function of A minus the mean value divided by sigma. An example of this is 3.9. So at this point, take a look in your textbook and view the video that's associated with example 3.9. The last thing I want to mention about the standard normal or the normal distribution is the 3 sigma rule. Your textbook has this figure in it, but it doesn't explicitly talk about the 3 sigma rule. The 3 sigma rule is very useful when we're trying to apply a random variate, or we're trying to apply a probability distribution to some random variate, but we don't know exactly what that random variate looks like in terms of probability distribution, but we want to somehow model it in a probabilistic fashion. Maybe we have some material and we want to find out what's the probability of strengths associated with this material, but we didn't do 1,000 different tests on this material, so we don't know what the probability distribution would look like. We don't know what the PDF looks like. We don't know what the CDF looks like. So what people do is they make the assumption, well, it's probably a normal distribution. Let's start there and see how that fits our data. So this arises from what's called the 3 sigma rule. If we take in this case, the standard normal, and we look at one standard deviation, the area that's associated with one standard deviation, in other words, the probability that we are between plus 1, and minus 1. That area is 68%. If we look at 2 standard deviations for our standard normal distribution, we find that we go from plus 2 to minus 2 in our area, and that now occupies 95%. If we expand that out to 3 standard deviations, plus or minus 3 standard deviations from the mean, we end up covering 99.7% of all of the area that's underneath the Gaussian distribution. So we've essentially got the whole thing. Now remember, it does go to minus infinity and it does go to plus infinity, but the probabilities that are associated with all of those values from greater than 3 and less than minus 3 account for only 0.3%. Very small amount. So the idea of the 3 sigma rule is, the 3 sigma rule means that if you are able to quantify what the mean is and the standard deviation, if you go out 3 standard deviations on either side of that mean, you will account for essentially the entire probability density of that random variable. So that we use this in practice when we estimate. So again, I'll go back to that material. Let's say that we have some material, and our material, we don't know what the probability is of the strengths of the material. We don't know what the probability density is, but we want to make some estimate of it because we want to do some probabilistic calculations. So we can say, all right, what are the extreme limits of our possible strengths of this material? So we could say that, I don't know, maybe the lowest value for our material, let's say, is equal to, let's make this easy, is equal to 0. It cannot be any lower than 0. That strength cannot be lower than 0. We can't have a negative strength. And the high side, let's say the absolute highest value that this material can have is probably 100. And again, I'm just making these numbers up. If these are the absolute limits, then these may correspond with these limits down here, minus 3 sigma and plus 3 sigma. If we're going to model it as a symmetrical normal variate, then the mean here is going to be the middle, so it's going to be 50. And the standard deviation is simply going to be that range of the smallest to the largest, in this case 0 to 100, 100 divided by the number of standard deviations that cover all of this. And this number of standard deviations that cover the entire range is 6. So 100 by 6. So now I have the parameters I need to model this. I have the normal distribution, the mean, and the standard deviation. So now for my material, I can make a first cut at probabilistic calculations by now having the parameters I need to accurately model a Gaussian distribution. And that's the 3 sigma rule. Very useful when you're doing approximations.